Okay, the problem is a crate is pulled at a constant velocity across the floor as shown. It has a mass of 50 kilograms. It's moving with a constant velocity of 0.5 meters per second. Whenever you see constant velocity, just, that's worth underlining. The applied force is 200 newtons to the right, and we move the crate from here to here 10 meters. And how much work was done by the applied force? What is the force of friction? How much work was done by friction? What is the crate's kinetic energy? And did the kinetic energy change? And where did the energy go? Okay, if you're watching this at home, pause it right now and then work it and then unpause it to watch the solution. Okay, so let's get going. Well, let's just do a quick give and find and solve here. I'm going to move this off to the side. So here's what we had that was given. Just redraw it really quick. Again, this was 50 kilograms. This is what I'd expect to see on your paper right here. 200 newtons, here's FA equals 200 newtons. The velocity is equal to 0.5 meters per second. It moves through delta x, which is equal to 10 meters. And what are we trying to find? Let's put it over here off to the side. Well, in part A, the work done. Now I use a subscript. Like when it's asking for the work done by a particular force, I just put W sub FA. Okay, just a shortcut way of writing it. For part B, we want to know what is the force of friction. C, what is the work done by the force of friction. And then D, the kinetic energy of the crate. And did the kinetic energy change? What was delta K? And where did the energy go? Energy. I'll just put a little question mark like that. All right. So let's solve it. I'm going to zoom out just a tad. Okay. Okay, so for part A, the work done by the applied force, well, that's equal to the applied force times delta x times the cosine of the angle between this force and this displacement. And we know all that. What's the applied force? It's given to be 200 newtons. What's the displacement? It's given to be 10 meters. Don't forget to think about the angle between them. Even if it's obvious, I always write it down to remind myself to think about the angle between them. Well, the force is to the right, the displacement's to the right, so the angle between them is 0. If I hook these two vectors up tail to tail, you get an angle of 0. Well, of course, the cosine of 0 degrees is 1. So it doesn't change this. And this is going to be 2,000, and a newton times a meter is a joule. That's my answer for part A. Now for part B, let's just do part B off to the side here. We want to know what is the force of friction. Well, I'm going to draw a quick little free body diagram of this guy. So this is a little bit of a review. mg, and you need a normal force, and then of course you have this 200 newtons like this, and you have this force of friction. You didn't really need to do this. You could have done this in your head. By now you should be able to do this in your head. You say, okay, well, if I sum the forces in the x direction, that'll equal ma in the x direction, and I look in the x direction, 200 newtons minus the force of friction equals, well, it's given in the problem that the velocity is constant. So there's no acceleration. So this is equal to 0. So m times 0 is 0. And so the force of friction must be equal to 200 newtons. And of course, this implies that the direction of it is to the left. Now let's do part C over here. The work done by friction is equal to the force of friction times delta x times the cosine of the angle between this force and this displacement. And here it gets a little bit trickier. See, and this is why I reminded you, hey, think about the angle between the force and the displacement. If I look at the force of friction, hey, it's just 200 newtons. If I look at the displacement, hey, it's still 10 meters. See, these are the magnitude of the force of friction, the magnitude of the displacement. But what's the angle between them? It's 180 degrees, right? I mean, because the displacement is to the right, but the force is to the left, so it's 180 degrees. Which means that it's negative 2,000 joules. Because the cosine of 180 is negative 1. So it just makes this negative. Yeah, Chris Osborne, it's for you. Okay, now for part D, what's the kinetic energy? This is pretty simple. It's 1/2 mv squared. So it's 1/2 the mass, which is 50 kilograms, times, oops, let's keep it on screen here, 0.5 meters per second, quantity squared. So what do you get when you do that? Somebody calculate that out. 6.25. 6.25. No. Kilograms times meters squared per second squared, which is a joule. Now it's not a watt. Remember, watt is the rate at which work is being done. Ooh, I could have included that in this problem, but I didn't. Now let's talk about this last part E, and it says, what's the change in kinetic energy? Well, you can just look at the problem and tell me what delta K is equal to. I mean, what is delta K? What's the change in kinetic energy going to be from here to here? Well, how fast is it going here at the beginning? Yeah, it's 0.5. How fast is it going here at the end? So the velocity hasn't changed, and the mass hasn't changed. 1/2 doesn't seem to change over time. It's always 1/2. So therefore, the final kinetic energy minus the initial kinetic energy, these two guys are the same. 0. We're not changing the kinetic energy here. Now the last part, it says, where did the energy go? Because when you look at the world and you look at problems with this concept of energy in mind, you have to account for the energy. Where did it go? Energy is not created or destroyed by any process. It's only transferred from one way of storing it into another way of storing it or manifesting in the universe. So here, this person pulled on this guy through 10 meters and transferred energy from his body into this moving crate. But the moving crate didn't gain any energy. What happened to it? It had to go somewhere. Okay, so this represents the energy that the person pulling tried to transfer into the crate. Okay, he or she tried to transfer 2,000 joules of energy into that crate. But now, how come this thing didn't go faster and faster? How come this work didn't result in more kinetic energy? Where did the energy go? Well, there was friction. And the friction took that energy away. See how this is positive work? Positive work means we're trying to put energy into the crate. We're trying to increase the kinetic energy of the crate. But friction took that energy away. Negative work. That means you're taking energy away from the crate. But where did that energy go? Okay, friction takes energy and transfers it into the environment and makes all the atoms around it wiggle a little faster. Okay, I mean, you know, if you take your hands and you rub them together, right, friction, what happens to your hands after a while? I mean, you know, why do you rub your hands together on a chilly February morning? To warm them up. That's where the energy went. It warmed up the bottom of the crate, and it warmed up the you know, from here to here. If you were to get a thermal camera and you went from here to here, you would see that, oh, the floor got a little bit warmer and the crate got a little bit warmer. So we heated the environment. That's what this kind of friction will do. This kind of friction, this sliding friction, will transfer energy into the environment, and let's see, Rachel Reese, this is for you, and it'll warm it up. Okay, now so that's the answer. Where did the energy go? It went into the environment in the jiggling of molecules. Okay, that's literally, if you gave me that answer on a test, I would give you full credit. You made the molecules jiggle a little faster. We call that temperature. We raised the temperature of the material here and here. Of course, you know, maybe some of the energy did work on the atmosphere with creating sound and all that. But, you know, anytime you change the environment, that took energy. This changed the environment as it went from here to here. It warmed up the floor and it warmed up the bottom of the crate. Okay? By how much? By 2,000 joules. When we get to chapter 12, we're going to learn about thermodynamics and so on. But that's what's happening. Any questions?